There's some music for you, Alex.
Awesome. Oh man, good to be back, John.
It is. This is really good to be back.
It's
I missed these our Wednesday nights together.
It was. I mean, it was what, about 3 weeks or so that we hadn't done anything like this. So
yeah,
it's amazing how that felt like forever ago.
Mm.
Well, it got cold quickly. The summer disappeared. Summer school's over, and here we are back at training again.
I wonder if my landlady can hear all this downstairs.
So how'd it go yesterday, Rickster?
Say again, sir?
How did it go yesterday? Were you doing class Take a Tuesday, or was it John?
John
Both
was.
of you. Oh,
It was
Both of us.
It was a group effort, and Rick had to be the closer.
I kind of asked out. I said, "You guys think the same thing I am?" I think John is like frozen permanently because we were waiting. I said, "Well, okay." So I finished on some points he was talking about buffer tanks, and I said, "Guess what, guys? We're already over time." I said, "You can watch me like change and put my slides on here and finish it up and be 20 minutes later than we should be." Anyway, it turned out okay. Again, I'll look and see what they wrapped up on those questions that you sent. There was a couple that I know I didn't answer. So, anywho, I think it turned out okay.
Yeah, it did. It did. So you're the new closer, Rick.
Closer. Oh boy.
Mariano Rivera, like McGrath just said.
We'll talk about it. Mariano Rivera is my favorite Yankee of all time because he blew the 2004 American League Championship Series.
Oh, come on.
It was the high point of my life, man. That was the high point of my life. All right. You know, they say, oh, next to my kids being born, this was better. This was better. What you say there, Tim?
I was going to say, do we think the Yankees take it tonight?
Probably.
Never ask a Red Sox fan
I'm a Cardinal fan. Yeah, I know he is. I'm a Cardinal fan, and they're winning right now, so I'm pretty happy about that.
Okay.
There you go. All right. Hey, it's good to see you. We got a lot of friendly faces and familiar names out there, so I'm glad everybody's ready and raring to go.
Raring.
All right.
See a lot of new names too, which is good. A lot of new people.
Yeah.
New blood. Fresh meat.
Fresh meat. New blood is good. New blood is good.
Yes, it is.
All right. Very good. Very good.
Not to be confused with young blood.
Right.
Yes. I can't get you out of my mind.
There you go.
You know the song.
I do.
All right. Okay. Well, let's tell Mr. Elton, Sir Elton, to pipe down here in the background. And shall we get this show started? Welcome back, everybody, to Takeo After Dark. It's so good to be back. And right now it is dark. I'm looking out my window, and it's 7 o'clock on a Wednesday night, and it's dark, man. Fall is almost here. When does fall officially start? That has already started, right?
Yeah, I think it was last week.
It was.
I don't know. I'm still indoors all the time. I have no idea.
Yeah. No, yeah, right. It doesn't matter, but yeah. So it's definitely different. So it's definitely Takeo After Dark, at least here in the East. I just want to say hello to everybody. John Barba from Takeo, along with our two regional trainers, Rick Mayo and Dave Holdorf. Rick is out in Utah, Sandy, Utah. Dave is on Long Island, and I'm sitting here in beautiful Exeter, New Hampshire, talking away to you in my nice dark room. And just for you, I see a lot. Again, we saw a lot of familiar faces here, or familiar names. We can't see your faces. A lot of familiar names that were with us both for the spring series and the summer series. If you were here with us with the spring series, a lot of this is going to be kind of a review for you because we're kind of repeating this is our factory training class, and we're doing it online because we can't do it. In person. Yeah, that's just the way it is right now. So Takeo After Dark is kind of an idea that John Messenbrink and I kind of came up with last March. to bring the factory training class online to as many people as we can. And the spring session was an amazing success. We had well over 200 up to 300 people in every session, which was absolutely fantastic. Then we did a little bit of a summer school program, and now we're coming back again with the evening program. So we're really excited to have everybody here and have you guys with us. The Take Go After Dark whole persona is kind of casual evening fun. So grab yourself, make sure you have an adult beverage with you, because we're going to have it. We're going to enjoy ourselves tonight. In the past, yeah, go ahead, Dave.
And a cigar if you got one.
And a cigar if you've got one. There you
Look
go.
at
And
that
Mr. Reichow, there you go.
Smoke 'em if you got them.
There you go. So yes, smoke them if you have them, and if you don't, go get one and smoke that. So our spirit animal, our guiding light, is maybe one of the classiest actors in Hollywood, Mr. Bruce Campbell, that you're seeing right there. And Dave is not wearing an ascot tonight, thank goodness. But we all have our own little T-shirts that are theme oriented. Tonight, Take Go After Dark, the fall edition, the first edition, is going to be on heat loss. We're going to start at the very beginning, as we do in our factory class. We're going to start with heat loss. As I mentioned, John Messenbrink of Mechanical Hub and I kind of put this thing together originally. And John can't be with us tonight because it's his anniversary and he's taking his wife out to dinner. Now, I don't know about you, but taking your wife out to dinner instead of being part of Take Go After Dark is questionable judgment, but it probably means he'll have another anniversary next year. So,
Yeah.
So probably a good move there.
Not
We
fully
have with us,
committed.
but yeah, we have with us Tim Ward from Mechanical Hub. And Tim, if you'd like to say hello
Hey,
and just
Tim.
give the audience a quick overview on what Mechanical Hub is all about.
John, thank you very much. Dave, Rick, it's great to see you guys as well on our third edition, partnering with you with this wonderful training that you're doing online with our team. And yes, John's out to dinner with his wife, and I hope they're enjoying themselves. Mechanical Hub, for those of you that are not familiar with us, Mechanical Hub Media, we have 3 websites, mechanicalhub.com, plumbingperspective.com, and hydronicshub.com. We've got a digital footprint with our social media channels. We're basically go-to digital service, digital space for the industry with content, plumbing, HVAC, mechanical, building services sector. So if you're not familiar with this, go check us out online, mechanicalhub.com, plumbingperspective.com, or hydronicshub.com. And once again, John, Dave, Rick, thank you for once again putting up with John and I every week with when we do these. We appreciate it, and we think you guys are wonderful partners to do this every Wednesday night.
Oh, it's definitely our pleasure, Tim. We really appreciate the opportunity to work with you guys and do some fantastic work. And maybe someday we'll get Eric Ani to.
I was going to say someday Eric needs to jump on.
He'll come down the golden staircase and mix with us regular people. That would be nice. All righty, let's get this show on the road. I want you to meet the crew. Tonight's theme, and we've done just for fun themes all along, is kind of Gilligan's Island. And I don't know if you can tell from my T-shirt. My T-shirt tonight is the SS Minnow seagoing charters. So since I've got the T-shirt, that makes me the skipper. All right, Rick, being the smartest of the three of us by far, is the professor, and
Yes.
Dave is Gilligan, not for any other reason that he was actually a legitimate sailor. He has seafaring experience. Dave is well, you're a graduate of what, the New York Maritime Academy?
Correct. Yes. Yep. And just underneath Throgs Neck Bridge for some of you East Coasters that know it.
All righty, and Dave has actually been on the ocean on a vessel working as a sailor and an engineer. So he gets to be Gilligan, not because he's Gilligan-esque, but he's actually the
Okay.
only one of us that's actually been on the ocean. So for you newbies, just real quick, if you're new to webinars, this is a different way of communicating and a different way of learning. So if you're new to a webinar, I want to make sure everybody knows how to use this stuff. On your screen, you should see a little orange arrow, and if it's pointing to the left, click on it. All right, that'll enlarge your control panel. It'll expand your control panel, and it'll make sure that you can hear us and make sure that you can ask questions and stuff like that. So again, it's kind of communication. We got to be able to hear. You got to be able to hear us. Make sure on your audio section you've got your speakers on and all that. Make sure that's all set. You can click on that section that you see there. We also have a handout section, and Dave, I think you put some handouts in here.
I have, yes.
Yeah, so just click on that and you can download the handouts. What handouts do we have today, Dave?
I put in the our catalog, our condensed catalog on the heating side of things. Oh no, actually the whole thing.
Okay,
The
putting
take,
in.
yep, we did the takeaways brochure, which we have some formulas that we talk about during the entire session over the entire 10-week session, and I've also put in the heat loss package that
Oh,
has the
okay.
H22 guide and whatnot. So you
Okay,
can
make sure
download. Yeah,
you
go ahead.
click on that, folks, and download that stuff. That's really important and very, very useful stuff. And then at the bottom, there's that questions and chat section. A lot of you have already found it, but this is how you're going to ask questions, okay, and communicate with us. So if you go to that section, you can just type in your questions right at this little point, this little gray area right there, and then click on send. So do me a favor real quick, just type in a hi, hello, how are you in that question chat section. And then that way I know you know how to do it. Okay, very good, very good. We got excellent. You guys
Oh
are
yeah.
awesome. You guys are awesome. And again,
And
this
if
is
you're watching this if you're using a device tonight, like your phone rather than a PC, you'll see a different way to do it. And across the bottom of the screen, you'll see a menu bar that's going to show you, how to set up your audio. Questions is usually right in the middle there. So you'll be bopping between the different screens and stuff. So you may not be able to see us or the presentation at the time. But you can see the questions and answers to do there at the bottom of the screen. And I'm sure I could see a few people already doing it from there too.
very good, very good. And from this little GIF here, this is another reason why Dave is Gilligan. This sums up our working relationship perfectly, I think. All righty, so let's get this show started. All right, let's get this program going. And since I'm the skipper, I'm going to get it going. When we do our program at the factory, we talk about DD equals MR. Now, understand this about hydronics, and we're going to start right from the very beginning here. Understand this about hydronics. Hydronics is math, okay? It's a science, so there's math involved. A lot of people in our industry either believe that they are math phobic, or there are folks in our industry who believe people in our industry are math phobic. They don't want to know about the math, and I'm not 100% sure I buy that. I struggled with math all through high school, but understand what math really is. Math is problem solving. And if you are a troubleshooter, and if you fancy yourself a troubleshooter, and most of us in this industry are, if you fancy yourself a troubleshooter, how do you think you learn those troubleshooting instincts? You learn those by solving math problems, because math is an orderly, step-by-step way to find a solution to a problem. So don't be intimidated by math. A lot of the math we're going to do today and throughout the course, you may never do. You may never do it, but you do need to know that it exists, and you.
Oh boy. Oh, no, it looks like John and JB. I think we lost you again.
We lost him. He's batting 1,000.
Oh man.
There he
Yeah.
is. You back, John?
Can you hear me?
Now,
Yep.
but
You
for
froze for
about
a second there.
10
Yep.
seconds there, you were gone.
Okay. Well, all right then. That's he's gone. He's back now.
You only got about 10 seconds out. You lost. So
Okay. All right. Good. Well, just understand this. Math is important. Math is what we're all about here. And the formula that we're looking at here, DD equals MR, is one of the more important math formulas in our industry. But for a lot of people, they've never heard of this. So when you tell them DD equals MR, they look at you and go, WTF? What's that? I've never heard that before. Well, let's examine what DD is. In our world, DD stands for diligent design. So what we're talking about here isn't a math formula, really. It's a formula for how to think about what you're doing. All right, this isn't about slapping stuff in and getting out of there and, hey, it works good enough, nobody's complaining, did my job. That's not what we're all about here. We're talking about diligent design. Let's do this right, because we have a van with our company name on it. We have a uniform with our company name on it and our own name on it. That makes us professionals. I mean, that we should be professionals. We're not handymen, we are professionals. So we've got to understand, respect, and utilize the math that makes us stand apart from the guys that just throw crap in. So DD in our world stands for diligent design. MR stands for maximum return. So DD equals MR is simply diligent design equals maximum return. That means what you get out of a system, the more you put into the system before you even enter the mechanical room, the better that system's going to be. The more work you do designing and thinking and making sure that system's right before you even step foot in the mechanical room, the better job you're going to wind up with when you're done. All right. So diligent design, do the freaking math. We're going to show you the math. It's not hard stuff. Addition, subtraction, multiplication, division. That's it. That's all we got. It's not that hard. And, you know, there's no square roots or any of that other crap. It's very simple stuff. It's just understanding where these numbers come from and what they mean. We're going to start that math tonight with heat loss calculations. We're going to show you how to really just do a simple one-room heat loss. We tried teaching this course without the heat loss, and the overriding question we get from people is, well, where'd that number come from? How do I know how many BTUs? Without that, you just don't have that information, right? So we got to start at the very beginning. And here's the thing, nobody teaches heat loss anymore. I blame software, I blame apps. Okay, everybody says, well, there's an app for that. Well, I don't need to know anything. I'll use the app, or I'll use the software, like the software is going to think for us. Software doesn't think for us. So we're gonna show you how to utilize the software as a tool instead of a calculator. All right. Once you have the heat loss calculations, then and only then can you get down to the real business of sizing the boiler properly, sizing the pipe properly, according to the load, according to the requirements. And then once you have all that, selecting the circulator properly, setting it up the way it's going to work so it'll work to its maximum overall system-wide efficiency. There's no such thing as there's one circulator is the only one you'll ever need. That's as much of a fairy tale as you have one ring to rule all the others, okay? It's just nonsense. There's no such thing as you stick a circulator in, press the button, and it figures everything else out for you. That's irresponsible to think that, to teach people that. You got to do it right. You got to know what you're doing. You got to know what you're holding in your hand and why. That's all part of diligent design. Really, folks, it's the differences right here. It's the difference between installing a system versus installing a collection of parts. I've said this, I don't know how many times in classes, and I'll keep saying it until they put me away. It does not take a particularly impressive skill set to put in a boiler, a bunch of pipe and fittings and circulators and stuff, fill it up with water, have it make fire, and keep people from freezing to death. That's not that hard to do. A reasonably competent handyman can do it, and they can do it for a hell of a lot less money than you can, all right? They can do it for a heck of a lot less money. So why would a customer want to hire you? It's because you know how to put in a system. You know how to pick the right boiler. You know how to size the pipe properly. You know how to select the circulators properly so they don't limit efficiency. They can actually enhance efficiency. You put together a system where the whole is greater than the sum of the parts. That's the point behind diligent design. That's the point behind the next 10 weeks that we're going to be working together. The maximum return, of course, there's that intangible of knowing that the job's been done right, and that's a good thing that's a good feeling to have, all right, a good thing to know. And a more tangible stuff, you can control material and labor costs. If everything is sized appropriately, it's going to cost appropriately. For example, if I only need 1-inch pipe instead of 1.25-inch pipe, well, that saves a lot of material costs. It's easier to work with, so that might save a little labor as well. A smaller boiler compared to a larger boiler, just going to be easier to deal with. All of these things have tangible benefits, all right? And ultimately, once a system is sized properly, it's going to work to its peak efficiency. It's not going to be oversized. It's not going to short cycle as much. If we put all the pieces together intelligently and carefully, we're going to have a better operating system, and ultimately better systems lead to greater profitability in the long run. So that's what the maximum return is. And there's a return for your customer. They're going to get a system that lasts long, that it works great, and it's priced right. All right. So DD begins with, of course, heat loss. All right. It begins with heat loss. So we're going to show you how to do a basic, simple IBR heat loss. Now, those handouts that Dave included that you can download, there's a heat loss design package that actually has all of these formulas. It has step-by-step instructions, and it has all of the appendixes that you can look up different U values for windows and wall assemblies and things like that. So that's all there for you for free. So make sure you take advantage of that. That's a very, very valuable thing to have. Also in the take away sheet, which is take away, we thought of that ourselves. There's a lot of other math formulas there and things for you to follow along with. So make sure you download all that and take a good look at it. So we're going to talk about heat loss, and there's a lot of methods. There's the excuse me, manual J. You can't say manual J without doing the sign of the cross. I think that's a rule. All right. There's manual J. There's all different. Every company has a software or an app to do heat loss. Here's the thing. All of those use the exact same math formulas. They have different assumptions. Okay. They have different shortcuts, if you will, but it's all the exact same arithmetic, the same two math formulas that we're going to share with you. And those two math formulas calculate two things: heat loss due to infiltration or air leakage, and heat loss due to conduction, meaning heat transferring from, from a warm surface to a cooler one, through a wall, through a window, through a floor, through a ceiling, heat loss by conduction. So those two math formulas are the two math formulas you're going to need for heat loss. Okay. At best, heat loss is an educated estimation, right? You take a look at a two-dimensional drawing, okay, and you're trying to, by using some estimations and using some numbers that you can cull from the design, you're trying to determine as best you can what the three-dimensional finished product is going to lose in terms of heat compared to the two-dimensional drawing, or based on the two-dimensional drawing. So at best, it's an educated estimation. And here's an important takeaway for you folks. I have never, ever, ever seen a heat loss done by the book, meaning no additional fudge factor put in, no extras here or there, none of that stuff. I've never seen one done that was strictly by the book that came up short. I've never seen it. There's so much fudge built into these formulas, to these calculations and these, approximations that we're doing. There's so much fudge built into it that we don't really have to add any extra. So, and you'll see that as we go along. All righty, so let's start with heat loss 101. I want to do a quick status check with everybody. How are we doing out there? Everything working okay? Just give me a status check. How's the pace, etc. Just type a little something in there. Let me know that I haven't checked out again and that you guys could still hear me and that it's making sense so far. So we got a
we
great.
still got you, brother.
All right, good. Okay, everybody's saying, all right, we got a guy says, I'm still awake. That's good. Okay. Oh boy, it's going to be, I can tell right now, this is going to be a good season. These next 10 weeks are going to be a lot of fun. All righty. Now, again, heat loss 101. As we said, all these different math formulas, all of these different heat loss calculation methods use the same two math formulas that we'll share with you. So they all use the same arithmetic, and they measure, as we said, air infiltration and heat transmission. Some terminology that we're going to need to know. First is ODT. That's your outdoor design temperature, your quote unquote coldest day of the year. This is where a lot of people put in a little extra fudge where they don't need it, because it's not, because they say, well, this is New Hampshire. It gets really cold here. Yeah, once in a while. I mean, it does get cold here. I lived in Minnesota. Boy, oh boy, it gets colder in Minnesota. We tend to exaggerate the outdoor design temperature because we don't want that phone call. All right. I can remember as a young plumbing and heating guy, our wholesaler did all of our heat losses to maintain a 70-degree temperature indoors at -10 outdoors. Now this was central Massachusetts. In central Massachusetts, I lived there 35 years. I never once saw it hit -10. The closest I ever remembered getting was about -1 for a very brief period of time over the course of 2 weeks in the winter of '93. I looked it up years later. The actual outdoor design temperature for that part of Massachusetts was 7 above, but we were designed at a 17 below. What were we doing? We were trying to be, so we don't want that phone call. We don't want that phone call, but we were oversizing systems. What's that old saying about the pathway to where is lined with good intentions? Well, this is where we're at. Now, ODT, outdoor design temperature, typically you get that, again, that heat loss package there, that we have a whole listing of different geographical areas where you can find what you should use in your neighborhood and where you are. And you might find that those numbers do in fact appear to be a little on the low side, meaning, hey, it gets colder than this. Well, that's intentional. Outdoor design temperature comes from ASHRAE, based on 90, 80 years of design data that they've looked at. And it doesn't represent the coldest it ever gets. Those numbers represent the 97.5 percentile of cold. What they're saying is 97.5% of the time, it doesn't get colder than this. All right. So that's what you designed to. Now, what's the problem there? What do you guys think the problem there is? Because 97.5% of the time, it doesn't get colder than this. What does that mean about the other 2.5% of the time? Well, it does get colder than that, right? If it does get colder than that, and these people are cold, oh my God, they're not calling ASHRAE, they're calling me. So we tend to exaggerate. You don't have to though. Because think about it. If you do a heat loss at 97.5%, and you come up with a heat loss of 57,421 BTUs, Rick, what are the odds of you A, finding and B, installing a boiler that has an absolute net rated output of 57,421 BTUs?
Slim to none.
Slim to none, right? What are you going to do?
Unless
gonna
you're the
go
boiler
up.
manufacturer. You're the boiler manufacturer, you got it made for you.
There you go. You're going to pick the brand of boiler you like, size up that covers it, right? Well, what if the brand of boiler you like, size up that covers it has a net output of 75,000? Well, right now you got about 18,000 BTU sitting around in that boiler looking for something to do. You're more than covered under design conditions. So don't get too crazy about that ODT or outdoor design temperature.
Now,
The other-
here's something else to think about too, about that 97.5%. So where I am on Long Island, outside design temperature is 14 degrees above zero. All right. So when I used to do tons of designs here on the island years ago, it was, I'd put 14 in. Oh, no, it gets colder. I'm like, oh, yeah, it does. What's colder than 14? When you talk to ASHRAE, the American Society of Heating, Refrigeration, Air Conditioning engineers, what's colder than 14? 13.99. Okay. So that got listed in that 2.5%. So don't worry, guys. Trust the number. That's the biggest thing I can say is to trust the number. Don't be afraid of it.
There you
Plus,
go.
we're in a global warming trend, right?
There you go.
Right.
There you
Right.
go.
And it was somebody's fault last night.
More terminology. Let's move right along, people. IDT. These are my guys. I got to keep Gilligan and the professor in line here. So IDT is indoor design temperature. That's the target temperature indoors. IDT. That's what you'll want to maintain. We're going to use 70 in our examples today. Now, the difference between ODT and IDT is called the DTD, O-da-do-da-day. DTD stands for design temperature difference. If you subtract your ODT from your IDT, that gives you the design temperature difference. It's the swing between the temperature you want to maintain indoors and that quote unquote coldest day of the year outdoors. What's that gap? That number is going to be a multiplier as we do our heat loss calculation. So that's how we come up with the DTD. We also have to find U value. Understand the term U value. U value is a measure of a material's ability to conduct heat. It's not a measure of your self-esteem. It's a measure of a material's ability to conduct heat. Now, in construction, do we want a high U value or a low U value? Guys, what do you think? Low, that's right. We want a low U value. Bill, Richard, guys, okay, very good. You guys got this stuff. We want a low U value. We want them as low as possible. We don't want to conduct heat very well from one side to the other. When it's hot outside, we want to keep the heat outside. When it's cold outside, we want to keep the heat inside. It's pretty simple. So U value is another multiplication number we're going to be looking at when we do our math, all right? So let's do a quick example. We're going to do this here room that you're looking at, 20 by 15 with 9-foot high ceilings, okay? Our indoor design temperature is 70. Our outdoor design temperature in this example is 0. That means our design temperature difference is going to be 70 minus 0 or 70. So our design temperature difference is going to be 70 degrees. That's the DTD. Now we're going to do infiltration first. Now infiltration is air leakage, right? Heated air. Over the course of every hour, heated air leaks from inside to outside, all right? And it's going to be replaced by cold outside air that we have to heat up. Now with the IBR method, or now it's called the AHRI method, that's the method I learned way back in 1988 at the Portsmouth, New Hampshire Holiday Inn at the traffic circle. I had a 3-day IBR class, and it was the most fascinating 3 days I ever spent learning about just about heat loss. I know more about Rockwell insulation than any man my age should. So this is all what we learned. But when we start with infiltration, all right, to measure infiltration, we use these factors or multipliers. Now, if you download that file, you'll see that there's IBR will give you 3 different sets of infiltration factors for the 3 different types of construction. They have this set of factors, which is normal everyday residential construction, your normal stick frame residential construction. They have another set of factors for, the really old, loose houses that are very, very drafty and leaky. And they have another set of factors for the super tight houses that every time you inhale, the windows go, and you exhale, the windows go, that kind of tight. So we have those different factors. This is for most normal residential construction from the 70s on through today. And these are multipliers, all right? And we choose our infiltration multiplier based upon how many outside walls in this room have openings, a door, a window, a skylight. It's not how many openings or how many outside walls we have. It's how many outside walls have openings. So if I have one outside wall with openings, I may have two outside walls in the room, but if only one of them has openings, I would pick 0.012 as my multiplier. What that represents is 2/3 of an air change per hour. IBR built these test houses many years ago, and they determined that a room with one outside wall with openings will lose 2/3 of its air over the course of an hour. It'll have 2/3 of an air change per hour. 0.018, we use that if we have two outside walls with openings. So two outside walls, I got a window on each wall. That's roughly one air change per hour. And then 0.027, I use that for three outside walls with openings or the main entry, the main in and out of the house. And that's roughly 1.5 air changes per hour. All right. I want to just dive into that a little bit more deeply here real quick. An example of infiltration. So let's say where these numbers come from and what do they represent? Let's say I've got a real little room, 1 foot by 1 foot by 1 foot. All right. To get the volume of air in that room, I multiply length times width times height. So length times width times height in this case is 1 times 1 times 1. That's 1 cubic foot of air in that room. Okay, it's a little room. And I have one outside wall with openings. Yeah, there's two windows, but it's just that one wall has openings. Okay, so I don't have to worry too much the fact that there are two. I'll do the window loss later. We're just talking about leakage right now. So one outside wall with openings. What that's telling us is, let's say it's 70 degrees indoors and 70 degrees outdoors. That's equilibrium, right? There's no real, technically speaking, there's no heat loss. It's 70 indoors, 70 outdoors, everybody's happy. Now, what would happen if it turned out to be 69 degrees outdoors? Now, technically, we do have heat loss. What's happening here is 2/3 of a cubic foot of air, 2/3 of the air in that room, in this case, 2/3 of a cubic foot of air, 2/3 of that 70-degree air is leaking from inside to outside, and it's being replaced by the same amount of 69-degree air. What 0.012 represents is the number of BTUs needed to raise 2/3 of a cubic foot of air 1 degree Fahrenheit in 1 hour. Okay, so that's where that factor comes from. 0.012, it's the number of BTUs needed to raise 2/3 of a cubic foot of air 1 degree Fahrenheit in 1 hour. 0.018, that's the BTUs needed to raise 1 cubic foot of air 1 degree Fahrenheit in 1 hour. And the other one, 0.027, is the amount of BTUs needed to raise roughly 1.5 cubic feet of air 1 degree Fahrenheit in 1 hour. Let me know if that makes sense to you. I just want you to where those numbers come from and what they mean. All right, know what they mean. Now let's go back, and here's your first heat loss math formula. It's length times width. This is for infiltration. Infiltration is equal to the length times the width times the height. That's the volume of air in the room, times design temperature difference, times the infiltration factor you've chosen for that room. And the cool thing about multiplication like this, you just do it in a string. All right, doesn't really matter what order you do it in either. It's just length times width times height times DTD times infact, and there's your infiltration. All right, so let's fill in the blanks. We know length times width times height in this example is 20 by 15 by 9. My design temperature difference is 70 degrees. I have one outside wall with openings, so my infiltration factor is 0.012. So 15 times 20 times 9 times 70 times 0.012. My infiltration heat loss when it's 0 degrees outside is 2,268 BTUs. That's the air leakage. I still have to do doors, windows, walls, floors, ceilings. So this is one element of heat loss. It's generally the largest element for each room. Windows will come in second, depending on how big they are. But that's generally the largest single element of heat loss for the room. So, all righty, Want to make sure everybody's happy with that. Does that make sense? Give me a little bit
Yep.
of feedback, man. Are we good
They're
here?
coming in
So-
saying thank you, makes sense, all that good stuff. So,
Hot dog, hot dog. All right, very good, very good. Now, I promised you guys a trivia question, right? We do have a trivia question for the night, and it's going to be a Gilligan's Island theme trivia question. And the trivia question for tonight is, and the way you're going to answer this trivia question is type it into the question section. We'll keep track of them all, and we'll pick if everybody gets if we got a bunch of people with the right answer, we have a little spinning wheel that Dave developed that we can use to select the winner, which we'll do next week. We'll announce the winner next week. So the trivia question of the night is as follows. Now, we know them as the Skipper, the Professor, and Gilligan's, but the characters themselves had full names. Now, I'm not talking about the actors. In the show, each character had a full name. I mean, the Skipper wasn't, he wasn't born to Mr. and Mrs. Skipper and they named him okay? He had a name. The character had a name. The professor had a name. All right. So what we want to know is, what were the full names of the Skipper and the Professor? And a bonus question here. This is the third part. What was Gilligan's first name? He had a first name. What was it? So the full names of the Skipper, the Professor, and then Gilligan's first name. That's a good one. We'll see how good you guys are. I know through the magic of Google, a lot of you guys are going to have it anyway. But that's just a little mental work there. Okay. So very good.
Don't
With
be
that-
Googling too long right now.
Yeah, don't be
get back.
Googling too long because you're going to miss all the good stuff here. Yeah. All right. So again, Professor, Skipper, and Gilligan's first name. That's what we need. All righty. All righty. Let us continue. We're going to do windows now. We're going to do our windows. Now, windows, everything from here on in is going to be, we're not dealing with volume of air. We're just dealing with area now. So we're dealing with area. So with windows and doors and walls and ceilings and floors, we're going to be using this formula right here. This formula right here. So it's length times width, that's the area, times the design temperature difference, times the U value of the specific item we're trying to calculate the heat loss for. In this case, it'll be the windows. Now, as we said earlier, U value is a measure of a material's ability to conduct heat, all right? And we want them to be very low. We don't want to conduct heat from one side to the other very well. Now, U value has a first cousin in construction, and that's called R value. R value and U value are in fact flip sides to the same coin. If I know the R value of something, like insulation, let's say, I can figure out the U value by simply dividing 1 by the R value. That will tell me the U value. So 1 divided by R equals U. Conversely, if I know the U value and I want to find the R value, 1 divided by U equals R. So 1 divided by R equals U, and 1 divided by U equals R. With Windows, it's easier to find the U value than it is to find the R value. Now, a lot of software programs have little wizards or pull-down menus and things like that, where you can look at something and say, okay, that looks like this kind of a window. Let's see what matches up to it. Bang, there you go. And that makes it pretty easy. Otherwise, you got to trust your eyes. The handout that we have for you lists a gajillion different kinds of windows and doors and things like that with the corresponding U values. You should be able to find something there. So so through that combination of those two things, you should be able to find out the U value for a wall construction, a door, a ceiling, a floor, a window fairly easily. So what we're going to do here, and aside from that, write this thing down, okay? This is the most common window there is out there. It's a double pane low E wood or vinyl frame window. The most common window in use has an R value of 2.77 and a U value of 0.36. So failing everything else, that's probably the most common window you're going to run into in normal everyday construction. All right, so 2.77, 0.36, okay? That's what we're looking for. So what we're going to do here, as you see, I have 2 windows, right? I've got 2 windows. Each window's 3 by 5. Now, there's a couple schools of thought here. If they are the exact same type of window, if they're both double pane low E wood or vinyl frame windows, If they're of the same window, understand length times width is area, okay? Now I could do this formula twice, once for each window, add them together, and there's my window loss. But area is area, right? 3 by 5 is 15 square feet. 15 square feet plus 15 square feet is 30 square feet. I could simply add the two areas of the windows together, and do this math just one time. It's going to give you the same number, okay? It's going to give you the same number. If it's a different kind of window, different type of window, then you really can't do that. But if they're the same type, make your life a little bit easier. Just make it one big window, okay, for when it comes to conductive heat loss. So in
John?
our, go ahead.
If they're doing that, that's great when they're doing it for themselves. But if they're going to give it to somebody to do plan review and somebody's going to look at your numbers, you might want to go ahead, because they're going to count windows, and all of a sudden they don't see as many windows as you have in there, and you start combining them. That just might save you a phone call or a rejection or something like that. That's my only point, is that
There you go. And that's
somebody else
perfectly
is going to
reasonable.
look at it, count your windows.
There you go. That's perfectly acceptable.
And then of course also it's there's one variable that you have here in all these houses. It's called homeowners. They get to change their mind on the size of the windows when the house is getting built. So if you can go back and change that one size quickly, rather than having to change, you don't remember which window that was. That's another way to do it too. I just use it as a CYA. Cover your ass as you're doing your designs and give it to somebody else.
Yeah.
Very good. Very
Yep.
good. All righty. So for our purposes here, we're going to do it my way because I'm the skipper. Okay. And we're going to do 30 square feet because it's easier that way. So I got 30 square feet times my 70-degree design temperature difference times my 0.36 U value. My window loss now is 756 BTU, 756 BTUs for the windows. Let's go to our next step now. That's the window loss. Now we got to do, we're left with the walls, the floor, and the ceiling. And the floor and the ceiling we don't necessarily have to. It really depends on the situation. But we've got to do the outside walls. So let's take a look at the outside walls. And we see we have two outside walls. That 20-foot wall is an outside wall. Of course, that's the one with the windows. And then this 15-foot wall is also an outside wall, but there are no windows there, but it's still facing the outside. Now, again, here's another way of looking at this. With walls, you want to do net area. Okay, with walls, we do net area. Why net area? Well, we already did the windows, right? Just take the window area out. If we had a door here as well, we would have done the door and take that area out. So we're dealing with just net area of walls, okay? So whatever we come up with for total square footage, we take out the window and door areas of whatever we've already done. So it's net area times design temperature difference times the U value. And what we have here, we have two outside walls, right? A 20-foot wall and a 15-foot wall. Again, we could do this, we could do each wall independently and then add them together. Or we could assume that this is just one big old outside wall, right? This is a 35-foot outside wall, and we can just count it as one outside wall. It's a 35-foot wall times 9 foot high. Again, I'm all about keeping this as simple as possible. So 35 feet long times 9 foot high, that gives me a gross wall area of 315 square feet. Now from that, we have to take out the window area, the windows that we just did. So we got to subtract the window area. So that's 30 square feet right off the top. And now our net area is 285 square feet. Now we have to figure out what the wall U value is. And unless they give you free rein with a Sawzall, you really can't, it's hard to know exactly what's in there. You can make some determination, some if it's a retrofit or a remodel, some educated conclusions as to what we have for insulation. And then once you know how much insulation is in there, and you know the R value of that insulation, you can very easily turn it into U value as we showed you. So for example, let's say this particular wall had 6 inches of fiberglass in there. 6 inches of fiberglass has an R value of 19. Now I know there's going to be sheetrock in there. There's some studs. There's the outside sheathing. There's Tyvek house wrap, and there's all this other stuff that makes up the wall assembly. And if you suffered through excessively rigid early toilet training and everything had to be just so, you can go ahead and measure all that and account for it and try to come up with it. Or you could understand that we're building a house here. We're putting a heating system in a house. We're not flying this thing to Mars, people. We're just trying to keep it, we're trying to keep it efficiently warm. In this instance, it's very easy to say, okay, I've got R19 in the wall. Let's work with that. You want some fudge? Here's a nice big old slice for you. So in this case, 1 divided by 19, we round it up. That's 0.05. Okay, 0.05. That's your U value. So now we're just going to do our multiplication string again. 285 square feet of net area times 70 degrees design temperature difference times 0.05 U value. That'll give me a wall loss of 998 BTUs. All right, so we're cruising right along here. But let me ask you, let me ask you guys a question. Did we forget something when it comes to walls, or did we ignore something very important when it comes to these walls? I'm going to ask you guys, and you guys see if you figure, did we skip something, and what was that? Type in your thoughts. Okay, when we did this wall heat loss thing, I'm going to see if you're catching it, and if you're still with us, and if I haven't checked out again. I think I have.
Oh,
I
you're
know,
good.
Dave, Rick, you're here? Yeah, okay, good. You guys can
You're
hear
good.
me. All right,
Yep.
very good.
Yeah, we got you, brother.
Very good, very good. So what do you guys think? Did we miss anything with walls? Did we miss anything with walls? Did we miss anything with walls?
Mr.
I can't
Tosco
keep
got
doing
it.
this. I can't keep doing this, people. All right. What do you think? Type something in. Give me
There
a
we go.
PR.
Nick Park did. Yep, we got a few. Yep.
You got a few. All right. Oh, here we go. Let me see. I got to scroll down here. Very good. Yeah. Boom, 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 boom. All right. Well, we didn't do doors. There are no doors. Okay. We're not worried about doors. Electrical outlets, Justin, that's all taken care of by infiltration. All right. Are we concerned about the direction? All right. Are
There's
we
several of them,
concerned
yeah.
about the direction?
Yeah.
Are we concerned about, is this north, east, south, west facing? Orientation, if you will. Are we concerned about that? No, we're not. Not with heat loss. With heat gain, we do care. With heat gain, we're concerned about the orientation. But with heat loss, we don't care. Because when is it coldest out, Dave?
At night.
At night. And Rick, at night it is
Dark, and the sun's
dark.
down.
And the sun's down, right? And that's
And I
dark.
love
The
your
house
old
doesn't.
saying.
Yeah, we have no calculation for lunar gain here, people. All right. We have no calculation for lunar gain. So we don't care about orientation when it comes to heat loss. We are concerned about orientation for heat gain if we're doing a cooling load. Okay. Now some interesting points came in here. Are we concerned about the wind? Oh, absolutely. Yes, absolutely. The wind is taken into account during infiltration. All right. The wind is taken into account during infiltration. Those factors, by the way, that I mentioned, okay, they were done by the University of Chicago. They built a bunch of test houses way back when, and they measured infiltration rates. But to give you a number, they had to make certain assumptions. And those numbers are based upon a 25-mile-an-hour wind blowing in all 4 directions at the same time. Okay. I don't know how that would happen. And if it did, which way would your hair blow? I'm not entirely sure. All right. So yeah, it's already, the wind is already taken into account when we do our infiltration heat load. Okay. Now, another question is the 998 the heat loss, the room heat loss? No, that's just the walls. Remember, we've already done infiltration. And to that, we've added the window loss. And to those 2 numbers, we're going to add the outside wall loss. What hair? Thank you, Michael. Ha, ha, ha. Very funny. I'm not the one you should be saying that to. It's these other 2 follically challenged guys you should be taking that shot at. I'm hanging in there, buckaroo.
I've just committed. I committed.
Yeah, you just gave up. What the hell, right? So no, we're going to be adding these numbers together. We can come up with individually. Like if this room had a door going to the outside, we would have figured that in. Walls and ceilings we're going to take a look at next. So I want to make sure everybody's kind of cool with that. Does that mean if everybody understands? Any further questions? And guys, if you could just scroll back there and see if there's anything we missed in terms of questions. But this was good stuff here.
Oh, I've been answering them. some of the guys were just wanted us to, so to speak, do it again. But I also wanted to let everybody know that we are recording these sessions. We will be able to next week, or actually not next week, tomorrow, you'll get an email with the link. So if you want to go back and review, but also they will be uploaded to Mechanical Hub's YouTube page, as well as Taco's YouTube page will be there also. You look for the playlists and you can find the recordings of these sessions. So you can always come back and review, even when you miss us tomorrow. Come and hang out
Right.
with us again. Yes.
Yep. So absolutely, yeah. You'll get this is being recorded, and you'll get a chance to take it. So there you go. Why did you guys only account for 2 walls and 1 out? There's one. Why did you guys only account for 2 outside walls? Because these 2 walls here, if I understand what you're saying, Peter, these 2 walls here are inside walls. The red walls are the outside walls. Okay, so those are outside walls. The other 2 walls were inside. So you don't do heat loss for inside walls because there's a heated room on the other side of it. It's not going to happen. So that's kind of why we just did those 2 walls. And when we did our infiltration, we did 1 outside wall with openings because only 1 outside wall had openings. All right, this wall didn't have any openings. Okay, so those kind of the little subtle nuances you gotta kind of make sure you take a good look at. Okay, make sure you understand there's little subtle differences when we're looking at walls and things. Alrighty, very good. Let's move on to ceilings and floors. Ceilings and floors. Same math formula. Length times width times design temperature difference times the U value. Length times width times design temperature times the U value of the floor or the ceiling. Now, let's take a look at what we mean. There are some guidelines. IBR gives you some guidelines when it comes to floors and ceilings. Obviously, with ceilings, you only calculate a ceiling loss if there's no heated space above, meaning it's an unheated attic or a built-up ceiling where the other side of the ceiling is the roof and the other side of the roof is outdoors. Those are the instances where you would do a ceiling loss. If it's a first floor and there's a heated second floor room right above it, you don't have any ceiling loss, so there's no reason to do a ceiling load there. Okay. If you were going to do a ceiling loss, length times width times design temperature difference times the U value. Now, again, I'm going to point you to that handout that we have for you. If you want to find some, for built up attics and things like that, they have all kinds of different things to choose from. So you just kind of see what you're dealing with, and then look in that listing of different U values for different ceiling constructions, and you'll be able to find something that will be close to what you have for a specific application. So that, again, terrific piece of information there for you. So with ceilings, you only do a ceiling load if there's no heated space above. In our example, we're presuming, okay, this is going to be a first floor room. There's a heated second floor above it. I don't need to do a ceiling loss. Floors are interesting. Floors are interesting, and IBR is very specific about this. And the first one's obvious. If it's like the second floor over a heated first floor, all right, second floor over a heated first floor, well, there's no floor loss there to speak of, so you don't bother doing a floor loss if there's a heated space below. If you're over an unheated basement or an enclosed crawl space that's like a mini basement, IBR says, you know what? You don't really need to do a floor load then either. And a lot of people get freaked out by that. But think about it. And then a basement, all right? A basement, it's not 0 degrees in the basement, right? It's not 35 degrees in the basement. It's more likely kind of a constant 55 or thereabouts. So if you were to do a heat loss for the floor, and you certainly could, if you were to do a heat loss calculation for the floor, you'd do 70 degrees indoors, 55 degrees below for a 15-degree design temperature difference. You could surely do that. You would find that the number will come out to be something so small that, it's like that heat load is going to be overcome by a person walking into a room, because your body with clothes on at rest or at light activity gives off 400 BTUs per hour all by its lonesome. Now, you got to do what you got to do to sleep at night. I get that. So your call on basements, unheated basements, or enclosed crawl spaces that are like mini basements, all right? You make that call. Now, if you're over an open or a ventilated crawl space where that temperature starts to get pretty darn close to the outdoor temperature, then you got to do a floor loss. You got to do a floor loss calculation there. If you are doing a slab on or below grade, then you've definitely got to do a floor loss there as well. And there are specific calculations for that. Again, that handout will have those specific instructions. We got a couple of interesting questions here. One is, how do you handle an unheated room like a garage? So it depends if you're not heating the garage, and that you're doing a heat loss calculation for a room that's next to the garage. What do you calculate for heat loss on that wall that's adjacent to the garage? Now that's a good question. For the most part, people, you have to make a couple of assumptions. We're closing the garage door. We're not leaving it open all the time. It's going to happen. It might happen, but there's not much you can do about that. What we have done, and there's a lot of different ways to go about it. What we have done, it would be to presume, if say I've got a 10-foot wall adjacent to the garage, what I do is figure that wall, 5 foot of that wall as unheated, and just do a 5 foot wall, heat loss for a 5 foot section wall instead of a 10-foot section wall, if that makes sense. That's kind of a nice compromise. Okay, it's a nice compromise. There are other ways to do it. Some people think, well, you pick a number. Is it going to be 40 degrees on that other side of the wall, 20 degrees, whatever you think it might be, and do that as well. I think it's two different paths to the same destination. How do you do a vaulted ceiling? How do you do a vaulted ceiling? You can do some geometry there and try to, do it in two separate pieces and find the volume. In terms of doing infiltration, I usually just square the room off. I just square it off. I say if the vaulted ceiling starts at 8 feet and goes up to 12 feet, I just figure that to be a 12-foot high room. Again, it's a heating system. It's not the space shuttle. So that kind of an estimation seems to be acceptable there. Yeah, the average height, I guess Richard McGrath says the average height. So yeah, just square the room off and you're good. And you can do some, and there's some other type.
12. John did say 12. You did say 12 before, but I know you meant 10. So
what did I say?
You said, okay, if it was a 8-12 pitch in the room, you said, all right, just pick it as 12. No, right. He meant to say 10.
I meant to say 10. Yes, thank you, Dave. I meant to say 10. See, I actually expected the professor to jump in there, not Gilligan.
No, I know the fudge factor ain't gonna hurt him, so I'm gonna let that slide.
All right, there you go. There you go. All righty, we are mopping what you're spilling, says Anthony. Very good. Okay, so let's go back to our job here and see where we're at. We've done everything. For our purposes, we're over an enclosed basement, so we're not going to do a floor load here. We're not doing a ceiling load. We're done. We just had infiltration, windows, and walls for this particular room. So infiltration, we had 2,268 BTUs. Windows, we had 756 BTUs, and walls, we had 998 BTUs. We add those up together, the total heat loss for that room is 4,022. And we call that BTUH-R, that's BTUH required, all right? When we go to heat that room, when we wanna put some heat elements in there, which we're gonna talk about next week, we're gonna figure out how do we put in 4,022 BTUs worth of heat into that room. And we're gonna look at baseboard, we're gonna look at radiators, we're gonna look at radiant floor, all these different types of options. And we'll be doing that next week. But that's kind of heat loss. It took a heck of a lot longer to explain it than it actually takes to do the numbers. What we found for heat loss is that it takes longer to get the information than it does to actually do the arithmetic. The arithmetic, even if you do it manually with a calculator, it doesn't take very long. But gathering the information, whether it's off a set of blueprints or whether you're measuring up a room or a house, that takes a little. That's what takes time. All right. So very good, very good. Let's take a look. We got some more questions here. What about the openings to the attic? Would that affect the heat loss in a room or a hallway? You're talking about an access hatch to the attic. Well, yeah, that would you know what? I'd count that as an opening. I would actually kind of count that as an opening, although again, it's not to the outdoors, but it is to an unheated attic. I know when we had our house buttoned up out in Minnesota. And one of the things they did was they siliconed the access hatch to the attic. It wasn't a usable attic. It was just built up. So they silicone that thing shut, so to lower the air leakage. So that will definitely impact your infiltration. So when you want to calculate for that, and you guys chime in if you have any other thoughts. I don't know if you just consider it another opening for that one particular area, that one particular room.
It's going to be more leakage, so infiltration should cover it, and infiltration is usually fat number anyway. So,
True.
you know, as long as they insulate that little lid, like mine, if I went upstairs right now, I've actually added a couple of sheets of 2-inch blue board that fit right on the lid, you know, so I could push it up out of the way. I don't have to worry about fiberglass and stuff like that. So from an R value standpoint or U value, it's pretty good.
Yep.
Again, it's that leak that's right around the thing. I'm not going to silicone mine because I want to go back up there. That's where my air handler's at. So anyway.
Very good. Very good. Alan, right. I question your units. BTUH equals BTUs per hour. Yeah, I'm guessing, Alan, you're an engineer. I'm just taking a wild shot at that.
Well, if you look on the screen, it's actually, you've got the slash in the wrong spot there.
No, that's where I put it. I think if we wanted to really get cute, we put another slash right there.
Okay.
It's shorthand. I mean,
Yeah.
I guess there's different ways to look at it. I know what I mean. So, but yeah, you're correct there, Alan. But I'm guessing you're an engineer, man. All right. Hey. I'm sorry, Dave. Didn't mean to poke it to you, Mr. I didn't. The Gilligan of engineers. Any possibility of starting earlier in the coming winter months? Now we're kind of locked into 7 o'clock right now. We're kind of locked into 7 o'clock, unfortunately, or fortunately. I'm not sure if that's going to be. We like to be consistent, so I think we're going to be starting at 7 though. But maybe for the future, maybe we can look at starting at different times. Okay, what else we got in here, guys? Because that is my last slide. Oh wait, I'm not done yet. The rest of the house. Let's quick do the rest of the house. 78,379 BTUs. I'm suggesting to you that this is a really large house, okay? This is a really, really large house. It's going to require 82,401 BTUs per hour. There you go. So there's our total heat loss for the house. I'm sorry, Rick, I didn't mean to speak over you.
No, just somebody questioning. They're talking about controlled ventilation, and they're giving him a number. That's what I'm interpreting. And as long as that number is less than the number we use for infiltration, we would have had it covered. But he's talking probably in the neighborhood of, you remember how we used to talk about ERVs or HRVs and how do we figure that in there? He's talking about nowadays they're asking for outside air requirements, so makeup air. And again, just figure which one's the greater. A lot of these heat loss programs will actually break it down. You just tell that room how many air exchanges an hour you're going to have. And so you can use that to help you out. Hopefully that answers the question. So.
Okay, yeah. It is interesting. When you talk about, mechanical ventilation, how does that impact what you calculate for infiltration? And I think you nailed it. We're not bringing in 0 degree air. That air is being tempered before it's being brought in. So it's mechanically controlled infiltration, and it's actually, if you were to math that out, I'd say that your rate of infiltration in that respect would be considerably lower than what we just calculated, as you said, Rick.
Yeah.
Correct. Now, I also like to throw this in too for everybody. So a lot of times what we do in the industry is we do the heat loss of a project and live with it. Now, back in our previous lives, the three of us were doing radiant floor heating quite often, a lot of designs there. And I looked at it this way. When you're doing a heat loss for a project and you've got to jam this amount of radiation into a space based upon that heat loss, we have an option right now, especially if this house is under construction. Renovation, or retrofit that you're adding something in, different story. But how can we change the heat loss of a house? for example, the old, when I would do a radiant system and the surface temperature of the floor would get way too high to handle what the wood flooring that was in there and the heat loss of the space itself. So we'd have to put in a supplemental into that space. We'd have the radiant floor as the primary heat, and we had to put maybe some baseboard or some fan coils in there. So now you go in there and say, all right, well, you have to spend X amount of dollars to go put in a secondary heating system. We can come along now as we're doing the designs and say, how about we up the insulation values in the wall and do some spray foam, or change the R value of the windows, or put a smaller window in or something like that. We have those options to discuss that with the homeowner. So just think of that also, the power that we have when you do the heat loss in this early stage of the construction of the home. So we can just make a better project all around.
Very good. Can you guys hear the train?
I didn't know what that
So-
was.
Yeah, it's the lonesome train whistle going through downtown Exeter. Alrighty. Here's a good question from Christopher. Are we taking insulation into account when we are calculating heat loss for walls? Would we account for less heat loss for better insulation? Absolutely. Remember when we did the walls, we had to find the U value of that wall assembly, and we presumed that we had R19 in the wall. To find the U value for R19 insulation, we did 1 divided by 19 equaled 0.05. So that's where we got that multiplier 0.05. So yeah, and if the wall had better insulation, if it had more insulation, or it had something blown in that had a higher U value or higher R value, we'd simply divide 1 by the R value. There we go. 1 divided by the R value would give us that U value. So it's all a matter of the U value at that point. As long as you get that number appropriate for the level of insulation that you have, Christopher, then you can math it out in that respect. In this example, we just presumed there was R19 in the wall. All right. So good. All righty. Very good. Now, so next week, we're going to talk about delivering the BTUs, whether we're talking about panel radiators, whether we're talking about fin tube baseboard, whether we're talking about radiant floor heating or other types of heat. We're going to talk about how are we going to get those 4,022 BTUs in there, and we're going to go into the charts. What do those charts actually mean? What are they telling us? And what kind of assumptions have we made that may not have been particularly accurate? So that's going to be next week. But before we get to that, I want to give you the trivia question answer. All right, the answer to our trivia question. We had a few people get it, and we're going to have to make a decision whether first names are acceptable, or did we want the full name? And that'll leave that up to you guys to figure out, Dave and Rick. We'll confab on that. But the trivia answer: the skipper was named. No, his name was Jonas Grumby, of course, played by Alan Hale Jr. But his full name was Jonas Grumby. Jonas Grumby was the skipper. The professor, played by Russell Johnson, was Roy Hinckley. Roy Hinckley. All right. And then Gilligan's first name. You had to hunt for this one. Gilligan's first name was Willie. It was never used in the series at all. The only place it ever appeared was on the cast list for the script written for the pilot episode. That's the only place it ever existed. So his first name was Willie. He had a first name. So Jonas Grumby, Roy Hinckley, and Willie. And Shane, you got that in right under the window there. All right, or right under the window? No, that's not right. Right under the wire. We'll call it that way. You got it right at the very end. We got it right in the very end. So that is our trivia answer. So we will see you all next week. Now, one of the things about Take-O After Dark is the three of us, we just simply decided to stay on for as long as you guys wanted to stay on, and ask questions. And we're happy to do that. So what I'd like to do now is I just kind of throw it open to you guys for whatever questions you might have, and I'll stop sharing my screen so we can get the webcams up. All right, and just open it up to you guys for whatever questions you might have on any topic at all, whether it's tonight's topic or anything else we've been talking, anything else related to hydronics, we're happy to just stay on as long as you guys want and yak away. All right. So we've still got 132 of you online still. So ask away. What do you guys? Let's throw it over to the professor out there in Sandy, Utah. What's on your mind today, Professor?
As far as what we just talked about,
Or just hydronics in general? What's on your mind right now?
you know what? I'm just nothing comes to me right now. Let me turn it over to Dave and give me a second to think about things.
All right, there we go.
Wow.
Dave, what's on your mind?
That must have been a good fun weekend or something like
Yeah.
that. He's still trying to organize his thoughts. Wow. Down in Mesquite there.
Yeah.
Oh, that's right. You were down in Mesquite.
So, I am quite surprised that we're getting back out there again, training wise. I'm glad we
You
had
are.
this many people here. Yeah. Well, even tonight for this.
Oh yeah.
To see as many people as wanted to come in, a lot of new faces, a lot of new names that I see on the list, and joining us tonight is really cool. And I'm really excited. John and I were talking about this I don't know, I guess about a month ago, maybe 6 weeks, and not sure what the fall was going to bring. And we said, all right, well, maybe we see 30, 40 guys. We just finished 20 some odd weeks of classes.
Right.
And we see, and everybody's coming back, which is great. And I started doing some live training. I was standing in front of people yesterday doing a training class on Long Island. Yes. So I was outside and we were all social distanced and stuff like that. We all had yardsticks in our hands and making sure going in circles.
Kind of whacking each other with them.
Yeah,
right?
yeah. And I'll be doing some more tomorrow over in New Jersey at Wales Darby's office in Jersey. So, so that was cool that, people still wanted to come in. Hey, it rained yesterday and people said, that's okay. I mean, we did have tents up and whatnot, but, I'm glad to get back out there and start seeing you all again. So, looking forward to getting back out there to seeing you guys.
Yeah.
I'm doing a trade show in Massachusetts next week.
Really?
An outside trade show / golf outing. So, with the PA.
Don should be on that one.
So,
Wait a minute.
Yeah.
I've done this trade show for the last couple of years. I don't play golf there. We actually have a table set up and we do a fundraiser and stuff. So that's a good time at that place. So, that usually takes place in August. They pushed it back to October this year. So
Golf outing doesn't call the boss to help out with the program. I'm struggling here.
you stranded me on this island, Skipper.
Yeah, well, no,
Yeah.
The skipper just got another pie to the face from Gilligan. That's what I'm telling you right now. God.
I don't plan this. It's not me.
You got a voice. You got a voice. Does Staco still have the system sizer program, the Flow Pro Designer program for heat loss? Yes, that still is available. We're not adding to it. We're not doing anything new with it or updating it or anything like that, but it is still out there and it is available for download on our website. It's a nice little program for heat loss. I never got that whole system design portion of it. We're supposed to do a takeoff for you and everything. To me, that never really flew seamlessly, but it's a really good heat loss design program where you simply draw the floor plan and it'll do the heat loss automatically for you, which I think is kind of cool. But that is available still on our website. If not, are there other programs that you can use? I've always been a lot of different companies have apps, and I don't want to disrespect any other company or feel like I'm ignoring any other company. Just the one I'm most familiar with is SlantFin's heat loss program. SlantFin's got a very easy to use heat loss app for your phone, and you simply plug in the numbers and it'll do the math for you and give you the information. So that's the most common one I see out there. Do you guys have any other favorites that you've used?
Well, we've taught on a couple of them. RightSoft's still out there, and they're real popular. And you guys keep talking about manual J. If you want manual J, make sure the software you're using actually shows that it is approved. And
Rick, you forgot. You have to,
oh, sorry.
every time you say
I
manual
wasn't,
J.
I wasn't Catholic, so
Doesn't
yeah,
matter.
I
Doesn't
forgot
matter.
that. You were, I wasn't. Um,
Still
and
am.
then of course, Avenir. They do a lot of people, especially the tubing people. They've gone out and done a good job of getting the tubing people to use their software. So Avenir, RightSoft, those are the ones that I'm familiar with and have used in the past. I haven't touched it in many years now, so I'd have to play catch up. But
I would, yeah, and whatever software you do choose to go with, I mean, like John said earlier when we started today, they all use the same math, all the same numbers get spit out at the end, right? But get comfortable with it, use it. If you're not going to do heat loads at least once a week, then find somebody to do it for you.
yeah,
Right? Find your
Mhm.
wholesalers. A lot of your wholesalers will have a heating guy on staff that's going to do it for you, and whatnot, and trust that guy and build that relationship with him. If you're not going to do it enough, I found when I was using RightSoft years ago, if you didn't do it every week, you forgot what you were doing, and it took you 3 times as long to get going with it. So
Right. Right. Yeah. That's the way it is with with software. You if you don't use it, you lose it. Right.
yeah,
That,
and if
again,
you
that's
have,
one of the reasons
yeah,
the manual stuff is pretty easy. That's a guys telling you down if you haven't done it yet, go to that handout section and download those files. You find it to be very, very useful. Here's an interesting question from Christopher. So outside of what Taco's doing here and Dan Holohan books, what are your best suggestions for learning about heating? Also, Sal Manzo says hello. Hello, Sal. All right.
hey,
Hey, back to Sal. All right. Boy, that's a great question. There's so many different sources out there for good information on hydronics. Now, you got to understand anything done by a manufacturer, and that's us included, is going to have that manufacturer's bent on it. That's just the way it is. We try to stay as generic as we can and give you guys respect your time enough to give you information. Yeah, we're going to eventually start talking about some Taco products as we go along here, but one of the things that kind of drives the three of us is we firmly believe that even if you don't buy a Taco product, ever buy a Taco product, you'll find information out of all of these programs that will help you. And that's really that's our promise to you. So what we get in return is that you listen to us talk about some Taco products from every now and again. And so that's kind of the bargain that we make with you. Now we've all gone to trainings before. I know when I was a contractor, I went to training before where it was put on by a manufacturer. I was really excited about it to learn something new, and then all I heard was our product's the best. The competitor's product's crap, and you'd be a moron to use it. And that's just a waste of everybody's time. You won't get that from us. I don't know about other people because there's some really good trainers out there. You look at some of the folks like from different boiler companies. Talk about one good boiler companies. NTI does a fantastic job of training. Weil McLean School of Better Heating, outstanding programs, absolutely outstanding programs on boilers and combustion and putting these things together and troubleshooting, which is always important. So both of those companies do fantastic. Peerless Training has always been very good. You guys know of any? HTP does a terrific job of training. Emerson Swan up in the Northeast with 4HTP, terrific job. So, do you guys have any others that you're familiar with or particularly favored too?
I'm guessing he might be talking about the books to learn on too, and you can't forget all of these that have been out there a while, right? So,
Right.
because he's referring to a book, that's what I was thinking anyway. So, lots of different reading books out there. Siegenthaler does a good job.
Mm-hmm. Yeah.
Holohan, as mentioned. So there's plenty of things to do self-learning for sure.
Yeah. A lot of different.
and
Go ahead.
I was saying, and also, find your local reps. I mean, these guys have a wealth of knowledge. They've been doing it for years too, and that's all they want to do. So any of our local reps that you have, they may also have training classes, doing their own, outside of what Rick, John, and I do. Find your local wholesalers. So there's a lot of opportunities to don't be afraid to go to the training classes. There's plenty of them out there. Yes, some of them might suck. we've all, you have to
Yeah.
go to some of them that's, that may not be what you were looking for. That the other part, any seminar you go to, be prepared. Don't
Yeah.
just show up. Just don't show up and say, okay, I'm here. Actually, research it a little bit. All right. We've got this internet right here in front of you on your device, on your computer, whatever the product is you're going to listen to, come with questions, write them out, be prepared, have that notepad, have that paper with you, the pen with you, and make sure you find out. And even if you have to, call the trainer beforehand and say, hey, what do you plan on going over tonight? Is it going to be an application style training, or is it going to be product based? And I'm not saying product based is horrible, but just make sure you know what your expectations are when you walk into that room.
Right.
That's, I think, is probably the biggest thing you can get out of any training class.
Ask the question too. Ask those questions. How many classes do us three, when we were actually standing in front of people, and we always give up, even on our webinars, we get plenty of opportunity to ask questions, and lots of times we get crickets. It's like no one says anything. It's like, we got to come break through this fear of asking a question that you might be embarrassed of. Every now and then we'll get that guy and they're the only ones asking questions. We don't want that either, right? We want everybody to say, hey, that didn't really make sense. I want you to clarify something for me.
Right.
Realistically, because the exact question you asked, 3-4 other people behind you were going to ask the same thing, and they go, I didn't have to ask. So be their hero and ask the question.
Yeah. I've written a couple of articles about this, with the best way to learn, I think, is to view it as work. You're working today. Yeah, you're not out on the job site, but today's not, your training day is not a day off. All right. It's a different kind of work. I always suggest guys show up early. There's benefits to showing up early. Number one, you get the best Danish, you get the fresh coffee, and you get to pick the seat you want. And God, don't sit in the back. I've had first guys show up, they sit as far in the back as they possibly can because they don't want to be noticed. That way I can sleep and you won't bother me. I said, what the hell are you doing here? If you wanted to sleep, stay home. If you really want to learn, sit up front. All right, sit up front and talk to the instructor. Instructors, for the three of us, we love it when guys sit up front and start chatting with us. I always like to go around the room and ask guys, what do you want to learn today? What do you want to learn today? Be the guy who has an answer for that. I've walked in, I've asked guys and say, what do you want to learn today? Oh, whatever you want to teach us. I said, well, that's putting a lot of faith in me, pal. I may want to teach you about something you have no idea. I said, the other guy said, what do you want to learn today? I want to learn everything. I'm going to disappoint you. We don't know everything. All right.
Yeah.
Go with a learning plan. What do you want to learn today? Why did you walk in here? What are the 1 or 2 or 3 things you want to leave here knowing? Okay. And then the other end of that, when you go there and you take notes and all that, that class doesn't end for you at that point. If that class ends at 4 o'clock, it ends at 4 o'clock for the instructor. It doesn't end for you. It ends for you in about 2 months. What do I mean by that? Studies will show that if you actually review your notes twice a week, every week for 6 to 8 weeks, that's a month and a half to 2 months after the session. If you review those notes twice a week, every week for 6 to 8 weeks, something magical happens. The retention rate jumps up into the mid 90% range. And it's also now not something you heard at some Yahoo say at a seminar. It's now part of your skill set. It's what you know. You own that information. It now belongs to you. And that's why you went to that class in the first place, isn't it? All right. And again, it's that thing. If you don't use it, you lose it. If you don't go over it, you don't remember it. A couple times a week, may take you 15, 20 minutes, go over the notes. So the investment you made of your time and energy to go to that class has a payoff. So again, for us, class ends at 4 o'clock. For you, you really want to get the most out of it. It's going to end in about 2 months. Just a different kind of work is all. Just a different kind of work. Here's a good one. Where does the name Taco come from? Who wants to answer that one?
Oh, I forgot to
And
bring
it's
it.
not taco. I got a guy out in Minnesota, a buddy of mine, he's in the heating business. He always, whenever he wants to get my blood pressure up, he says, hey, I want to get one of them taco pumps. I said, yeah, Brad, I've got a taco right here for you.
Hard shell or soft shell?
Hard shell, that's right. It's Taco, obviously. And the name comes from the original name of the company. It's an acronym. And the acronym stands for, gentlemen,
Thermal appliance.
Appliance Company.
Thermal Appliance Company. That was the original name of the company when it was started back in 1920. All right, the Thermal Appliance Company. The first product the Thermal Appliance Company made was a rather large sidearm water heater that connected to the side of a boiler. It had a big old copper coil in a tank, and it heated up. It was a hot water, it was a water heater. It was a sidearm water heater, an indirect, basically. And big thing, plenty of room to cast the full name of the company into the side of the thing. Thermal Appliance Company, man. Plenty of room, plenty of room. That thing was a fantastic product. It became the industry standard for decades. For years, when people referred to a sidearm water heater as a Taco heater, it became like Kleenex. It was a generic name. But that was the first product, so plenty of room for Thermal Appliance Company. The second product was an offshoot of that first product, which made a considerable amount of really wicked hot water. There you go. Dave's got the picture of that thing up there. It made a significant amount of incredibly hot water that led to the development of our second product, which was the mixing valve to temper that water down so you don't burn people to death. That's a lot smaller. It was only like this big. A lot smaller than that. You didn't have room for the Thermal Appliance Company, so they had to shorten it to TACOs. Big T, big A, big C, little o. And people just started calling it Taco because this was 1925 or something like that. Unless you were within a mile or so of the Rio Grande, you had never heard of a taco, right? So it didn't occur to anybody to call it a taco. They said, oh, Taco, okay. And that's where the name came from.
Yeah. T-A-Co. Taco.
Taco. There you go.
Yeah.
There you go. So there you go. If you're ever on Jeopardy, William, you're gonna win that. You're gonna win the big prize. All right. Very good. What's the app called? Joe is going to ask the app. The app is
The one for the heat loss.
Yeah, it's not an app for us. Ours isn't an app. Ours is it's a program that you can download. It's called the Flow Pro Designer. The Flow Pro Designer. And if you go to our go to our website and under software, there's a software section. You'll find all different kinds of pieces of software that you can download, but the one specifically is called Flow Pro Designer. Flow Pro Designer.
I included a link in the chat section.
Oh, very good. You the man. All right, and it will not run on an Apple. There you go. That's right. It's not. It's really PC only. Boom, 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 boom. Here we go. Anything else? Yeah, we get the Calefi Hydronics series. Yep, another good place to learn. Let's see. Appreciate you guys putting in the effort to help people. I'm an old engineer, so this is mostly review, but I was hoping for my new guy could attend and then he could discuss tomorrow. I'll be back next week. Excellent. Good. Very good.
Good deal.
Excellent.
Yeah.
All right.
And also, where else do you want to learn is hopefully we'll be getting back to our 2-day factory classes also.
Yeah, there was a question earlier about when we might be doing that again. Not this year. Ain't gonna happen this year. I'm hopeful next year. Hopeful, not optimistic, but I'm hopeful next year because it's just a matter of what kind of restrictions are we going to have on having people in our factory and what kind of appetite is there going to be for people to actually come and spend 2 days in a factory with other people. I'm not sure where that's going to go. Nobody knows where that's going to go. So it's going to be a wait and see. We're budgeting for it. We're planning for it. I'm just not sure what's going to happen.
Stephen Garvey's got a clarification there. He's talking about looking at heat loss, but that's what we did. We did a heat loss calculation, Stephen, and you're wanting a heat gain calculation for your air conditioning system. So, some other questions will come into play like orientation, window, all that good stuff. I hear that train now. I hear my train coming. Who was that?
Coming around that bend.
No, not that one.
Oh, I hear that train coming.
Jimi Hendrix.
Oh, there we go. Not Johnny Cash. Different guy.
I didn't grow up on Johnny Cash.
How about Mystery Train? Or Paul Butterfield.
Mystery Train.
There you go.
No. Anyway, so does Stephen, do you get what we're saying? You want to use a software that takes all that into consideration for doing heat gain calculations. So hopefully that helps.
Very
Rainbow
good.
Bridge. Carl nailed it. That is in fact, it's hard to get that album. It's really hard to find that anymore, as a matter of fact.
All right, very good. What else do we have here for questions? I genuinely thought it's because you guys like tacos too much. Name the company Taco. No, Peter, we didn't.
And it's because burrito was too long.
Yeah, burrito doesn't fit on a pump very well. Yeah. All right, what else do we have? I wanted to see about heat. I'm sorry, Stephen. Yeah, you've got that. You just handled that question. Bum, ba, bum, 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 ba, bum, bum, bum. What else? Ever do shows in Canada? Oh gosh, all three of us have gone have been north of the border
We
from
miss you guys
Scotia
a
to
lot.
British Columbia. Yeah, whereabouts are you in Canada? As we'd like to, yeah, we've done I've done all three of us have done multiple presentations throughout Canada. I've done Winnipeg, been Thunder Bay, Ontario, all throughout Toronto and Southern Ontario. I've done a few in Nova Scotia. I don't speak French, so Quebec is kind of out. But where you guys have done several as well, right?
I've been in your neck of the woods, Colton, in Newfoundland, but I haven't been there in a while. So there have been plans to try to. I was going to be up there quite a bit this past year. So we were making plans back in January with Sean Giberson, our national sales manager up there, and I was going to do a lot of work.
Canceled
from Toronto
everything.
East. Yeah, from Toronto East. I had it all on the schedule and everything. So I've been there. Yes, and interesting little island out there, Newfoundland.
Newfoundland,
yeah.
Rick, you've been quite north of the border quite often too, right?
Indeed.
Yeah.
Mostly west, the 4 territories. So province, I should say. So been good. I miss you guys. So it's always fun.
Very good. Pump versus circulator, asked Shane Brown. Well, technically it's a circulator. It's not a pump, it's a circulator. We use pump as shorthand, and we probably will, but it's a circulator. And the difference is a pump pumps and a circulator circulates. Circulator has a lot less work to do. Pump's got to do a lot more work.
Yeah.
So there's that difference. A circulator's got a pretty easy job. Here's the difference. A pump is like a bicycle pump or a well pump. It's got to lift stuff. A circulator just makes stuff go round and round. The circulator is more like the motor on a Ferris wheel, if you will. All it's trying to do is overcome the friction loss of the bearing assembly that holds the wheel to the frame. It doesn't have to lift anybody up because there's some other guy in a cart on the other side going back down. So it's a circulator is very much like the motor on a Ferris wheel, whereas a pump is you're lifting and pressurizing. So they're very different things. Pump is for open systems, circulators for closed systems. That might be the easiest way to do it.
So, a pump is moving something from point A to point B. Water pump. We're going from here to there, where a circulator is doing it from there all the way around, right back again.
Right. And we don't have to worry about lifting or height or anything like that. So yeah, and we're going to call them pumps because it's just shorthand that's been grilled into everybody's brain, but it is a circulator. I had a very good friend of mine from Seattle, and I went into a long discussion on why they're circulators and not pumps. You know who I'm talking about, Bill Leonard, one of my favorite people on the planet. And every time I use the word pump in every training class ever since then, he would correct me. And I didn't kill him.
You wanted to.
And for a short period of time, but Bill's a sweetheart of a guy, one of my favorite people. So.
He's still at it too, by the way.
God bless him.
Last time I was up there, he came to a training. But one thing, like the other 2 members of this 5-member team, you're looking at 3 of us. If you talk to those guys in the commercial world, we have 2 trainers that are pretty much strictly commercial. Those guys call them pumps, man. Even though they're circulators, they call them pumps. Yep. So again, there's people that'll get real tricky on you, and they'll call it a rotodynamic and instead of centrifugal. And all we say is, hey, centrifugal circulators fall in under rotodynamic. So if you guys get really picky, anyway, there's all kinds of stuff out there.
That'd be a great name for a band.
Rotodynamic?
Yeah, the Rotodynamics.
Yeah.
I like that.
That's what we'll be.
Yeah, it'd be yeah, that's us. We're like ZZ Top, but just with a lot less hair, facial hair. Although you guys, never mind, it's not going to work. It's as an analogy, it's just not going anywhere.
I'll show you a picture last winter. Remember, it was about down to
Oh
here.
yeah, that's right. That's
I
right.
cut it off.
That's right. Yeah, that was the Santa Claus as a young man look.
Well, no, the old man.
The old man, Santa Claus, an old man. There you go.
Old man now, because it's all white. Okay.
Yep. All righty. Very good. Very good. So again, did we get? Are there any questions we didn't get to here, guys?
77 people still on with us.
That's it. You guys just you can't get enough. Are we that engaging? Maybe we are.
You got to ask the question, or we're leaving quick.
There you go. There you go. Yeah, next week's going to be kind of interesting. We're going to break down. Into discussing what do these specification sheets for like cast iron radiators or baseboard. What do they really mean? What all these columns and rows of numbers. We usually for baseboard we have our default number that we always go to at 500 BTUs per foot. Well, is that the right number to use? What are we looking at here? So we can be a little bit more precise. And then we're also going to say, say we had some cast iron radiators here. What's the potential output of these radiators? How do we know how many BTUs these things can put out at different water temperatures? If I look at, and we're going to talk about sections of radiators, tubes versus columns, how to figure out, the square foot of EDR or equivalent direct radiation, et cetera. So we're going to cover all that next week. I think it'll be kind of interesting. So we'll definitely have some fun there, and we have fun every class we do. So that's kind of where we're at. All right. Okay, well, let's see if you guys got any more questions. Please type them in now, or else we'll say thank you and so long for a wonderful evening. We do thank you so much, guys. It really is gratifying that such a large group of you guys came out to spend a night with us. I know one of the things about TACO, and our owner Johnny White does like to come to these programs every once in a while and sit in and talk with you guys. But I think one of the things that is most important to us as individuals, I know these guys well enough that I can make this statement for them, is that we just love spending time with people. We love spending time with you guys and talking with you, not as customers, but as fellow people. We're all human, and we're all in this together. And that's what makes these things so much fun. And your participation, even though you're just writing stuff out here, your participation makes this really gratifying for us and enjoyable for us. But hopefully, I hope it makes it enjoyable for you as well, and that you're getting something out of these programs. That to me is a successful class, is when we leave here feeling that we've made some connections, and you guys leave with not only with good information that you can use starting tomorrow, but with a connection with other people, with the other people in the class, and with us. So I hopefully we can accomplish that again this year.
Always good stuff. Always good stuff.
Very good. Well,
I've got something to throw out there just for to chew on for some other conversation. But in the days and the times that we're in where we're doing variable speed circulators, keep in mind, just like when we do our heat loss calculation, we're designing for the worst case scenario, as John did a good job of showing you that. What is that day that it's really cold out? When do we need the most heat? And we size for that. And we understand that only 2.5% of the time do we even need that, right? So everything else is less than. In the world of variable speed circulators, guess what? Same thing applies. We're sizing pipes for a pump that's seldom, if ever, going to be pumping that many GPM. Especially now that we put a pump on a system, it actually knows what the pressure drop is. And just like we had talked about earlier, when we do estimates for heat loss, we only know what the heat loss is once we've done, for instance, like a blower door test on that structure, right? Then we realize our infiltration rates are sky high and got a bunch of fat in them. And the same thing applies on our pressure drop estimates, right? We do a pressure drop estimate, we calculate, not just an estimate, we calculate, but still most of the time there's enough fudge in there, that number is actually high. So I wanted to throw out the thoughts of looking at pipe sizing from the standpoint of somewhere in between. There's all kinds of savings that can be brought on by doing something like that, knowing that the circulators are mostly oversized, etc. So I want you to chew on that. Some other time, bring it up if it's something that kind of catches your mind to talk about. I've thrown it out to our engineering department about looking at things from the standpoint of averages and not the maximum or the extreme. And there's some things to be gained by that, talking about velocities and things like that. But anyway, food for thought. I thought I'd throw it out there for sweet dreams, so to speak.
Very good. And while you're doing that, we got one more question. This is from Randall Hobby. Best way to compensate for a room that is occupied by a lot of people at once, like a break room or a room that has a large amount of product. Storage room, therefore, doesn't have as much volume. Interesting. That's one of the things about Manual J and all of the appendices that follow. The Manual J is about this thick, okay? And in reality, Manual J just has those two math formulas that we showed you. It's the same thing, but how does it get to be this thick? It's designed for engineers to calculate specifically, okay, this room with an occupancy of 100, heating it's not really a problem, cooling it is, keeping and ventilating it is. So there will be steps for that. Understand each individual person is going to give off about 400 BTUs per hour, right? So you got to take that into account when figuring your cooling load. And then there's factors for electric lights and everything else, all other ancillary equipment that's going to be giving off heat. That's just, you start getting into some serious engineering when it comes to heat loss there. And that's why Manual J is like that thick, but then there's Manual H, Manual G, Manual F. There's so many addendums to that you got a stack of books like this where you would be looking up different factors or different instances that you're talking about, Randall. I guess short answer is all that stuff can be looked up. And that's the cool thing about it. There's a math formula for everything.
You can find it. Yes. Yeah.
Yeah. There's a math formula for all that, but the professor couldn't fix that hole in the boat. What's that all about?
Yes. So you can make electricity with a couple of coconuts, but couldn't fix a hole. Yeah.
Hey, here's a professor to answer that same question, though, looking at it at a different way. I don't know if I'm right or not, but it says best way to compensate for a room that is occupied by a lot of people. Well, the best thing to do there is your initial set point needs to be lower than what you think it is, right?
Mm-hmm.
Churches are prime example of this. People congregate, right? They come in and all of a sudden 400 BTUs times 200 people. Well, you don't want a set point when they walk in the church of 70 degrees, right? You actually probably want about a 60 degree. They go, oh, it's kind of cool in here. Oh, just wait a minute. Yeah. Wait till we start singing, So just you understand where we're going with that. If you want to compensate for gathering or a room that has nobody in it for really long times and then all of a sudden is completely populated, then you have to lower your set point temperature. Otherwise, guess what they're going to feel? Too warm.
Yeah, it's gonna be too hot.
Yep. Yeah. You could be running air conditioning in the middle of the winter.
In the winter, yeah, right. Crazy.
And we used to have to try to design homes for that back in the radiant days because homeowners wanted that floor to be 85 degrees all the time. I don't care.
Yeah.
Well, it's too hot in here. Well, now you got to turn the air conditioning on. Wait, what? It's 30 outside. Yeah, it's too hot in here. But your floors are on. Yeah, I want that. So yeah, I had to do a couple projects like that. Yeah.
Yep. That's the way it goes.
Yeah.
Oh, the good old radiant days.
Yes. So there was Bjorn it was wondering if we could do another example of doing heat loss, but it remembered another opportunity for me to see a different way. Instead of seeing the same heat loss again, we do have FlowPro University, which is our online e-learning system that John and I have put together. And it has individual sessions going through there, but it's not just a video that you sit and watch. It is interactive, so you are asked to answer questions as you go through it. So take a look at that on our website. If you click, go to the takeocomfort.com, click on training, and you'll see the online training called Flow Pro University, and find the heat loss section there, and it'll go through it in a nice step-by-step detail too, compared to, and again, like we said, this is also going to be replayed for you tomorrow.
Yep, there you go. And in addition, actually, I think it's on our YouTube page. Is Takeo After Dark, the summer session. The part 1 was also on heat loss, but we did a different project.
Yeah, more in depth.
And we got into a little bit more depth in that one application, actually, Bjorn. So that would be a good one to look at too. So it's Takeo After Dark, the summer session, part 1. That might give you another thing to review.
And 2, I think didn't we cover it in 2 also?
I don't think we might have.
You know, it was like
part 1
that was a continuing design. Yeah. Oh, that was heat loss. Then it was design, stuff like that.
Right. So part 1, we started on heat loss. Then everybody had the homework to do after part 1, and then part 2 we went over it for the whole house. Yeah.
I didn't see it on our YouTube page, so I don't know if I got uploaded there. But then go to Mechanical Hub site, get it from those guys. So let me, before we break down here, let me go get the link for you there.
Oh, I got something I can throw in here too. Hold on. I'm going to have a link for you here, Bjorn, that you're going to be very happy with.
A link with a wink.
A link with a wink.
Oh boy.
There you go. Okay. This is going to be, I sent that privately to you, Bjorn. That link should be coming up to you, and I'm going to put it in the chat. This is a link to actually all of our stored Takeo After Dark recordings going back to last year. So that's been sent out to everybody here, and it's sent in the chat section. So check that out, and you click on that. That'll bring you to a web page that has recordings of all of everything we've done so far. And this recording will be added to it tomorrow. So hopefully that will help. Cool beans, man. All righty. Well, cool. Last call now for questions. Every time I say last call, we get some new questions. So that's pretty cool.
Keep saying it.
Keep saying it. There we go. Last call for questions, people. All right. What's the difference between summer school and today? Well, summer school, we just different curriculum, if you will. We just had a different approach. We talked about some different topics.
We had guest speakers coming in.
Yeah.
So we took designing a system a little bit slower.
Mm-hmm.
And not as much, like when we do these classes now, it's an application based, but it's also going to have that product in there too. But we also went into, like John said, other topics. We went into electrical understanding with Carol Fay, and we had boiler chemistry, and we did combustion analysis.
Yeah, water quality.
Water quality, which we don't do for the normal class. Yeah.
Right. Stuff that wasn't specific to any Takeo stuff. We don't make water treatment or boiler, water treatment products. We don't do combustion analysis, but we brought in experts who do know that stuff to help guys learn about it. So that's kind of what we did there. All right, cool. All right, folks. Hey, thank you all. This is good. Yep. Really good time to say good night, and we shall see you all next week.
Same bad time, same bad channel.
Good night, everybody.
See y'all.
Alrighty, bye-bye.
Gilligan, Professor, we'll see you down the road.
Sayonara.